is our circuit diagram, which is we use Multistage to design it. We use Multistage using a 15 volt DC rail. Our input is a 10 mV peak, 1 kHz AC signal with a 1600 ohm source resistance. For the stage 1 is a common source MOSFET amplifier biased by a voltage divider. This stage provides a very high input resistance, so we don't load down our signal source. For the stage 2, we use 10 microfarad coupling capacitor like SKEE capacitor to block DC bias between the stage while letting the AC signal pass. Stage 2 is a common emitter BJT amplifier designed to deliver high voltage gain. Notice that we split the emitter resistance by passing only RE to VC4 to stabilize our AC gain before feeding the final output for our 20 kilo ohm load.
Now, let's move to the DC operating point analysis of our multistage amplifier. In DC analysis, the fundamental rule of capacitor is that they act as perfect open circuit. This is because, at DC, the signal frequency is 0 Hz. A frequency of 0 yields an infinite AC resistance. It will completely blocking any DC current from passing through. Let's verify this directly by using Multistage. Now, let's see our operating point. So we can see IC1 until IC5 have exponents. Because the number is very microscopic, we can assume IC1 until IC5 is open circuit. So, to be more precisely, we can see from our circuits from at this point and then at this point. So we can see the voltage is different between these two. So we can assume this acts as a open circuit.
Now, let's move on to the AC waveform analysis by running a simulation to see how these coupling capacitors handle our time domain signals. First, let's look at the green sine waveform. We can see that this is our voltage input, which is our pure AC input signal from our source generator, where its peak is about 9 mV voltage. Next, we can see the yellow sine waveform, which is our V output, and we can see that the voltage output at its peak is about 18 millivolts. This is a visual demonstration of what a coupling capacitor does, which is allows the fragile AC signals to pass through effortlessly.
Assalamualaikum. So next we go to the calculating, which is we have two parts, which is the DC analysis and the SKEE analysis. So for DC analysis, we also need to do both parts, which is the MOSFET and the BJT. So for MOSFET, we need to find the operating point, which is the VDSQ, IDQ, and the VDSQ, which is we use the formula and the KVL loop. So here we get the VDSQ and IDQ, the value is here, and the VDSQ we also use the KVL loop, which is here is the answer. So for the BJT, we also use the KVL loop, which is we need to find the IC. So we use the KVL loop to find the IB, and then we use IC equal to beta IB, we get this answer. And for the second part, which is SKEE analysis, first we need to draw the mid frequency circuit, as you can see there, and then we need to obtain all the information to calculate the voltage gain, which is the GM1, GM2, R pi, and then the impedance is ZI, ZB, ZI2, and ZO. So for the voltage gain, to find the overall, we need to find each one of the voltage gain, which is AV1 for the MOSFET and then AV2 for the BJT. And then we need to multiply the value, and then we get the overall voltage gain, which is we get 15.3299, and we also can put it into the dB unit, which is we get 23.711 dB.